Alright, so today we are starting chapter 8. Like I said, we're going to start it with exponential growth. A lot of what we're going to be doing today is graphing exponential growth functions. We're also going to learn some new vocabulary words that you'll hear a lot for the rest of the year. We are doing lessons every day this week, except on Friday you will have a day to work on homework. So Tuesday, Wednesday, Thursday, we're just going to get right into lessons. But Friday we'll slow it down a little bit and let you guys catch up. Any questions on what this week looks like?
Those are real ACP marks.
Our ACP for 2 weeks.
Here's some vocab you're going to need to know for today. The first one, and you will hear this a lot from here on out, is an asymptote. An asymptote is a line that a graph approaches as it moves away from the origin. Usually graphs don't touch asymptotes. We'll look at a couple where they cross over the asymptotes. But it's usually just a line that your graph approaches. Usually as it goes to positive infinity or negative infinity, it will approach an asymptote. And the other thing you're going to hear today is an exponential growth function. Exponential growth functions are written in that form that you see right there. Y equals A times B to the X. Notice that A is not the one with the exponent. Sometimes you won't see A. Of course, A is 1 in that case. B is the base, and then X is the exponent. Here's a little bit more about exponential growth functions. Again, that's the form you'll see them in. Y equals A times B to the X. When it's in this form, the graph passes through the point 0a, meaning that a is the y-intercept. The x-axis is the asymptote of this graph, so as you get away from the origin in one direction or the other, it will approach the x-axis. The domain is all real numbers. The range is that y is greater than 0 if a is greater than 0. Whoops. That says the exact same thing. You can probably guess what it should say. This should be less than and less than. Excuse me for that typo. So if A is positive, all your y values should be positive. If A is negative, all your y values should be negative as well. And be careful of any graph transformations. All of these 4 bullet points just apply to the basic A times B to the X. Of course, if they're adding 3 with the X, we know that everything would go left 3. Or if they're adding 4 on the end, we know everything would be bumped up 4. So, of course, there are some changes that could occur. But in general, these are the properties for exponential growth functions. So here's our first example. In this example, we don't see an A. Remember, A is the number in front of the base that has the exponent. 2 is our B, that's our base. So A in this case is 1, if that helps you kind of figure out what's going on. Remember, our y-intercept is at 0a, so we know it'll go through the y-axis at 1. The easiest way to start these is to just do an xy table. Remember that we said the domain is all real numbers, so you can plug in any numbers you want. But you should only be getting positive numbers out. So if you're getting some y's that are not positive when your a value is positive, you made some sort of mistake. So I'm going to start just by plugging in the numbers right around the origin.
Are those random?
They're just the numbers 2 to the left of the origin, 2 to the right of the origin. So -2, -1, 0, 1, 2. Now, remember, when you plug in a negative as your exponent, you're actually taking the reciprocal. So when you plug in -2, that's actually 1 over 2 squared. 2 squared is 4, so 1 over 4. When you plug -1 in, again, that forces you to do the reciprocal, so it would just be -1 in your exponent. With a 2, gets it a 1/2. When you plug 0 in, 2 to the 0 is 1. We already talked about 1 is your a value. In this case, that's also your y-intercept. And then you can see when you plug 1 in, 2 to the first is 2, and 2 to the second is 4. And you could keep going, you know what happens, so it's going to shoot straight up. That's why you call them exponential growth functions, because they grow so quickly. Once you start plugging in exponents like 3, 4, and 5, your x or your y values just go straight up.
Is this the hardest it gets?
This is pretty easy example for what we're looking at today. All right, let me point out a couple things before we take questions on this. We talked about how the x-axis, we call it an asymptote here. An asymptote, it said, is where your graph approaches as it goes away from the origin. So as you go to the left, do you see how the graph is getting closer and closer to the x-axis? It will never actually touch the x-axis. It's just getting closer and closer and closer. If you plugged in negative 100, if you did it in your calculator to the negative 100, you'd still get a positive number. It'd be a very, very small decimal, but it would still be positive. You are never going to get below the x-axis here. That's your asymptote. Okay? We look at horizontal and vertical asymptotes. This is a horizontal asymptote. Any questions on this one? All right, here's another one.
So Alg2Adv negative?
Mm-hmm. Yes, in this case, our A value is negative 1. 4 is our B. So this is like negative 1 times 4. 4 is what you're taking to each exponent, and then you're making it negative. It's not in parentheses, the negative 4. So A in this case is negative 1, so I know my y-intercept is going to be negative 1. I also know, like Sydney said, that all of my outputs should be negative. If the A is negative, all your y values are negative. If A is positive, all your y's are positive. The x-axis should still be my asymptote here. And now we just start plugging in. So if you did negative 4,
Negative 1 to 1/16.
very good. Negative 4 to the negative second power, it's like doing negative 1 over 4 squared. Remember, it forces you to do the reciprocal, which is negative 1/16. So it's very close to the x-axis, not hitting the x-axis yet. What happens when you plug negative 1 in? Negative 1/4, good. So we're getting a little bit further off the x-axis, but still pretty close. When you plug 0 in, 4 to the 0 is 1, and then times the negative 1. That's where our A value becomes our y-intercept. A is negative 1. A is whatever you're multiplying the base by. So if this was in parentheses, negative 4 would be that B value from that form we were looking at. But since it's not, it's like negative 1 times 4 to the x. So you do 4 to the x times negative 1. When you plug 1 in, of course, you're just going to get negative 4. And then you can see it goes down very, very quickly to negative 16. And then you can connect those. Remember, some of you went a little crazy with your arrows on the last test. Just make sure that this way it never crosses the x-axis. This is an asymptote. It does not go above the x-axis here. This one is kind of crazy. It's pretty dramatic. But just be careful with that x-axis direction. What questions do you have on this?
We're allowed to use a calculator.
Of course. Yes, I would encourage the use of calculators. All right, here's another one. Do we have an A value here?
Yeah.
What is it?
Negative 3.
Negative 3. This one's a little easier to see that we do have an A value and it is negative, so all your outputs should be negative. We should still have an asymptote on the x-axis. And we can still plug in those basic 5 points right around the origin. This is a lot of calculator work, so I won't bore you with it too much, but remember the -2 makes the 2 squared go to the bottom. The -3 would stay on top, so that's how we get the -3/4. And there we go. So it's still approaching the x-axis. Not as quickly as the previous examples, but still make sure you don't go above that x-axis. If you're worried about it, you could plug in a big number, like I said, -100. You should still be staying right below the x-axis, so that is your horizontal asymptote here. For example 4, we can also see that we have an a value. The a value other than 1, you always have an a value, sometimes it's a 1. Here our a value is 4, so I know it's going to go through my y-axis at 4. It's also going to cause all my y values to be positive. If a is positive, so are your y values. Again, we can just start that xy chart. Now, if you wanted to do -2, -1, 0, 1, 2, that would be fine. This example was taken straight out of the book, so I just used the ones that they used. It helps you show just a little bit more of how that graph is approaching the x-axis to the left. But if you didn't have those exact points, you should still see the basic shape. But there we go. Now, you can also see how the a value is related to those graph transformations we looked at last week and a little bit back in November. You're basically just taking the first graph we did 2 to the x, and you're multiplying all the outputs by 4. So if you want to go back to that, that might help you out here. Anytime you can relate it back to a graph transformation, it should make things make a little bit more sense for you. Any questions on this one? Alright, so here's number 5. It's starting to get a little tricky. But remember, if you can keep in mind what we know about graph transformations, it should help you out a little bit on this one. So before I even do an XY chart or anything, I just want to think about what's going on. What's my A value here? -3. So I know all my outputs should be negative. I also know that I will have a y-intercept at negative, well, it actually won't be the y-intercept. Normally we'll have a y-intercept at -3, but remember this graph transformation is going to throw things off a little bit. So you can kind of imagine the general shape of it and then just apply this transformation. In general, what does adding 4 to your input when it's with the x, what does that do to your graph?
Makes it 2.
Moves it to the left. So this, we should have pretty much the same graph as when we did -3 times 2 to the x. It's just going to go left 4. And that's exactly what it's showing you right here. So we have done this graph before, right? This was number 3. You're basically taking what you did in number 3 and you're moving it left 4 spaces.
What if you actually did the problem?
It should work out the same way. So this is the transformation method. So I am just moving the whole thing to the left. So just shifting all your points to the left. Do you guys remember in an XY chart how you would move everything to the left? Side to side changes are your x values. So you could actually just take the x values from number 3 and subtract 4 from each one of them because you're moving it to the left. All right, I'll show you the XY chart on the board in a second, but I do want to cover domain and range too. Domain is still all real numbers, and the range is still just the negative values because our A is negative. So the only thing that's really changed between example 3 and example 5 is now we moved left 4 spaces. So can someone remind me, I'll just put a little number 3 What was our XY table from number 3?
-2, -1, 0, 1, 2.
Okay, and then what were our outputs?
-3/4, -3/2, -3, -6,
-6 and what?
-12.
-12. Okay, so for this new graph, to move something left, you are changing the x values. So you would just subtract 4 from each x. So now we have -6, -3/4. -5, -3/2. -4, -3, -3, -6, and -2, -12. So if you want to double check those, they should all work. You could even just plug in -1, -2, 0, 1, 2. The problem is, look how far you're down into the negative already. So that might not be a very good method, but you can see I'm too far in the negative and then just start plugging in values to the left. But anytime you can pull things back to what you know about graph transformations, it's going to be a whole lot easier. So here's number 6. Again, if you can think back to any transformations that will help us get a starting point, that would be great. I see that I'm multiplying by 5 in the front, so that's going to multiply all my y values by 5 if I can find a graph similar to this one. I am subtracting 1 with my x, so that's going to move it right 1. So if I can keep those things in mind, that would be helpful. So if you can start with this graph, I don't think we've done this one before, but it's still pretty simple to do. So just looking at this new graph, I am not worrying about the -1. I'm going to deal with that in a second. If I plug 0 in here, 2 to the 0 is 1, 1 times 5 is 5. Remember, your a value is always your y-intercept when you're not doing the transformation quite yet. So it's going to look something like that, right? In general, that's just a very general basic sketch. What would I do to that graph now in order to make it look like this? Move it to the right. Minusing. Subtracting 1 moves it to the right. So you could basically take that graph and just bump it to the right. A lot easier with a computer. But that should give you a general idea what your graph is going to look like. Again, anytime you can bring it back to your transformations, that will be very helpful for you. If you just wanted to start with an XY chart, that would work too. However you want to do it is fine with me. We do need to state our domain and range though. You can plug in any number you want. The domain's all real numbers. The range here, since A is positive, it's still just the positive values. The only thing that's really different is just that shift to the right. Now, to be honest with you, if I was doing my homework or a quiz or a test, I would still do an XY table just to make sure that the graph was a little more exact. But this is just kind of a general way, just reminding you of those transformations you already know. Any questions? All right, so looking at number 7, I can very quickly pick out some transformations that are happening. Here they're subtracting 2 from the x. Remember, subtracting 2 makes it move right. This one's the opposite. Right 2. And then adding something on the end makes it move up. So if you could graph the basic y equals 3 to the x, move that graph right 2 and up 4, you should have this. Or, of course, you can just start with the basic xy chart. You should end up in the same spot we do. I like the transformation method. So if I plug 0 in, I'm getting a 1. If I plug 1 in, I'm getting a 3. Of course, if you plug 2 in, you're getting a 9. When you're plugging negatives, you're getting fractions, so you're getting closer and closer to the x-axis without crossing it. So in general, y equals 3 to the x looks like that. That's not my final answer. That's just kind of a starting graph that I can work with. Now, that graph, I want to move it right to and then I want to move it up 4. Now, as I said, that's a lot easier for what I'm doing using technology. I can just pick that graph up and just shift it. You guys can't really do that paper and pencil. So again, just kind of think of the y equals 3x as a starting point and go from there. Or just use an xy table. Now, this is a really interesting one to use domain and range on. Which one did I change, the domain or the range? The range. Did you say range? Oh, no, range. You can still plug in any number you want, right? Domain's what you're plugging in. You can still plug in negatives. You'll get fractions, very small fractions, but then you're adding 4 to those. So the domain's not changing. You're still plugging in all the numbers, but you're not getting any numbers less than 4. Look at the graph. See how it's approaching 4, 4, 4, 4, but it's not going to cross it? So your asymptote here is at 4. The line y equals 4. So all your y values are going to be greater than 4. And again, that's because our asymptote is usually the x-axis, but if you're bumping everything up 4 because of our graph transformations, that bumps all your y's up 4. Here's number 8. This is probably the last one we'll get to today. Some obvious transformations going on here. Our base is a 4. It looks like our a value here is going to be a 1. The adding 2 in the exponent will move it left. And the subtracting 3 on the end will move it down. So if I can graph 4 to the x, and then move that graph left 2 and down 3, I should end up with this graph. Or again, start from scratch and do it that way. So if I plugged 0 in, I would get 1. If I plug 1 in, I get 4, and then 2 in, you get 16. So you're shooting very quickly up. Again, anytime you go to the negatives, you're just getting fractions that are smaller and smaller and smaller and smaller without quite hitting the x-axis. So that is the graph y equals 4 to the x. Those are very easy to graph. Just plug in a couple things. It's a lot easier to graph than something like this, because now I'm going to take this graph. The adding 2 causes me to move left. Good. So you can just pick it up and move it left. A lot easier with technology. And then the subtracting 3 is going to move it down. So it's magical. Now, the important thing about these transformations is what it does to the domain and the range. So are my inputs any different? Has it limited the things I can plug in for x? No, you can plug anything in for x now. Are all my outputs staying above the x-axis like normal?
Isn't it y is greater than 3? Or less than 3? Okay, greater than or equal to 3? Greater than
Negative 3, good, you were so close. Yes, so instead of now staying above the x-axis, it's staying above negative 3. So all of your y values are greater than negative 3. And again, if you're not quite sure where your asymptote is, remember that's where it's approaching, plug a really big number in. Plug 100 in here, and you'll see that it's almost going to be negative 3. Not quite, but getting very close. What are your questions on this stuff? This is getting pretty tricky. This is what I would consider upper level algebra. So if you're struggling, just stick with it, ask questions, you'll get there. But any questions you have at the moment? Here's your homework. Again, Friday we will have some in-class time to do homework. But I would not wait until then. Like I said, this is getting into upper level algebra stuff. It's pretty tricky, so make sure you're keeping up with it. Ask questions if you need to.